Alright, let's have a look at letter D. Sigma n equals 0 to infinity when factorial x to the n. So for this couple of exercises, we're going to go back to the ratio test as opposed to letter C, in which we use the root test instead to simplify work. So let's see. Let's set it up. That's the limit of a sub n plus 1 over a sub n as n approaches infinity. That's the limit n approaches infinity of the absolute value of n plus 1 factorial x to the n divided by n factorial times x to the n. In this case, no multiplication by reciprocal. This is fine. N plus 1, right? So that's the limit n approaches infinity. Okay, let's start simplifying. Recall that when it comes to factorials, let's focus on the largest of the factorials and start simplifying from there. So in this case, the largest of the two factorials is the n plus 1 factorial. So I'm going to write n plus 1 n factorial because that matches the one in the denominator. And then this x to the n plus 1 can be rewritten as x to the n times x to the first and x to the n in the denominator. So let's simplify whatever we can simplify. N factorial over n factorial, x to the n, x to the n. So this will be the limit n approaches infinity of, in this case, we're going to be left with n plus 1 times x. Alright, remember, just recall like what we did with the previous examples, we're dealing with a limit in terms of n, not in terms of x. So this x will go outside in front of the limit, rather absolute value of x, limit n plus 1. But in this case, n plus 1 is infinity. So what is this? Okay, this means absolute value of x, limit n plus 1 as n approaches infinity is infinity. Alright? Well, in this case, how do we force this to converge? I mean, because we're getting infinity. Alright? We're getting infinity. That means that when the limit is infinity, the radius of convergence is 0. Alright? Because it doesn't matter in this case what x is. Could be really big, could be really small. Times infinity will still be infinity. Alright? Because the limit is infinity, the radius r equals to 0. Okay. How did I get that idea that when the limit is infinity, the radius is 0? Okay. Think about this. So you're standing at whatever point yourself, and you want to move freely to any other place, So, but in some cases you may have limits. So you can, if you have limits, you cannot go very far. So, but in the situation in which you have infinitely many limits, then you cannot go anywhere. You can only remain at your center, like the series remains only at its center, that is, converges only at its center. At its center, x equals 0. Alright? Okay, another way to explain this, okay, so let me take it from here, and guys, let me warn you about this. What I'm about to do here is forbidden. Why? Well, you'll see why it is forbidden. So when I do absolute value of x times infinity, okay, I'm still going to set this inequality. I'm gonna set it as an inequality and set it less than 1. And then I'm going to solve the inequality for absolute value of x. How do I do that? Well, let's divide both sides by infinity. I know this is crazy. This is what it's forbidden, because we're not allowed to do any arithmetics or algebra with infinities. Cancel the infinities. Okay, in this case, this is the forbidden part, because we are assuming that both infinities here are the same, and it's not the case. And well, 1 over infinity is 0. Okay, so this is another way to say that the radius is 0. But again, guys, keep in mind that this is, what I did here is, it's forbidden. And I did it just so you can see an alternative, you know, an illegal way to determine. So please don't do it on the test. So the minute that you see the limit is infinity, then the radius is 0. All right, let's look at one more example and see what we get. So sigma n equals 0 to infinity x to the n over 2n factorial. So again, set it up as a limit using the ratio test. So that's a limit x to the n plus 1 to n plus 1 factorial times 2n factorial over x to the n. Now from here, let's see. Let's start simplifying this. Okay, of course, distributed 2 to n and the 2 over n and 1, and that's going to give us the limit n approaches, whoops, what happened here? Okay, limit n approaches infinity, absolute value. Okay, this x to the n plus 1 is the same as x to the n times x to the first, and this is 2n plus 2, the whole thing factorial, times 2n factorial over x to the n. So from here we can actually, number 1, divide out the x to the n's. And the next step right here is to work with the factorials and simplify them. And again, keep in mind that what we do is to work with the largest of the factorials. So the largest of the factorials in this case is the 2n plus 2. Limit n approaches infinity. That's an x over, okay, so that's a 2n plus 2, 2n plus 1. We keep going, 2n factorial, because it already matches the one over here. And okay, that's simply over 1, right? Or simply, yeah, let's leave it like this. So let's simplify. We can just go about dividing out the 2n factorial with the 2n factorial. That equals the limit n approaches infinity. That's x. That's an x over 2n plus 2, 2n plus 1. And recall that our limit that we are computing, the limit that we're computing is only in terms of n, not in terms of x. So this x goes outside as absolute value of x times the limit of 1 over 2n plus 2 times 2n plus 1 as n approaches infinity. And this limit goes to 0. So what do we get? Absolute value of x times 0, which in this case, well, 0 times any number is 0, which happens to be less than 1. This is true all the time. And well, this is what the book explains, every single book. But I mean, from here, what the book tells you, oh, if you get 0, that's always less than 1, then that means that the radius is r equals to infinity. And well, so comparing with the previous example, limit is infinity, radius equals 0. Limit equals 0, radius is infinity. Well, what's the other way to explain this? Well, number one, so the limit is 0, so you are standing at a given point. The limit is 0, that means that you don't have any limits. How far can you go there? How far can you go then if you don't have any limits? Well, that means you can go anywhere. That's why the radius is infinity, because you don't have any restraints, you don't have any limits. So converges for all x. Now, what's the illegal way to explain this? Because there's always this illegal way. So I'm going to take this and I'm going to set it the forbidden way. All right. Okay, let's do less than 1. Okay, so what I'm going to do here is to divide both sides by 0, which we are not supposed to do, right? Cancel the zeros, that's what we're not supposed to do. All right, and then what's 1 over 0? Well, it's undefined technically, right? Because, well, in this case, this is the same as analyzing the function f of x equals 1 over x, which looks like this. All right, and notice that if that 1 over x, it's undefined. Even the limit, you know, it would be d and e, because exactly at 0, both limits from the left is negative infinity and from the right is positive infinity. However, for our series, we're looking for the positive side of the graph. So in this case, this is, and that's why the radius is infinity. But again, this is the illegal way. This is the forbidden way to explain it. So don't do this on the test. So I think it's just, I don't know, maybe like a funny way to see it, but the incorrect way. So this is going to take us back to the original, or rather to the very definition on page 3. The series converges only when x equals a. That is when the radius equals to 0. No, actually when the radius is infinity. Converges for all x when the radius equals, or not the radius, rather the limit. The limit is infinity. And the series converges for all x when the limit equals to 0. And then for the other cases, well, we already did many cases, you know. I mean, at the beginning of the section, I could have just told you, oh, if the limit is infinity, well, the radius is 0. If the limit is 0, well, the radius is infinity. And then for the other case, just test the endpoints. But it was important to first see how these functions of series look like, how they work, and see the different cases before coming up with a summary. And this is the end of this section, and this is a good place to quit.